We're going to discuss what are the forces acting on a person riding an elevator. So in this situation, the person is sitting on a chair and the elevator is at rest. So what are the forces acting on the person? There is gravity acting on him, which is the mass times 9.8 on Earth, which is 784 newtons. Since he pushes down on the chair pushes up back on him with the same force, which is what we identify as the normal force. And since the person is at rest and in equilibrium, the normal force must be exactly equal to the force of gravity in magnitude. So we identify that to be as 784 newtons as well. Now let's take a look at what happens if he takes a ride to floor 10. So notice what happens to the normal force. It increases and then it decreases and then comes back to the normal. So what is really happening here? In order to understand that, so when the person, let's represent this as the person. When the person is accelerating upwards, the forces on him are still the same, the weight and the normal force. So the weight is still 784 newtons. However, the normal force has now to be larger than the weight, so that the difference in the two gives rise to the net force, which causes the acceleration. So the normal force minus mg is your net force, and this net force is what provides the acceleration. So the net force is equal to ma. So when he is accelerating upward, the normal force can be rewritten as ma plus mg. The normal force is the force with which he pushes down on the chair, and that is a force with which the chair pushes up back on him, and that is a sensation of weight. So that is why we refer to this as the apparent weight. So notice that the apparent weight in this case is greater than the actual weight because it's mg plus ma, which is why, going back to the simulation, we see that when he is accelerating upward, the normal force increases. Then, because he went from the first floor up to the 10th floor, he has to first speed up from rest, and then he goes at a constant velocity. When the velocity is constant, the normal force and the gravitational force are going to be the same. That means you feel your normal weight. And then when he comes to the 10th floor, he has to stop. And in order to stop, if you're moving upward and you want to stop, you have to apply an acceleration downward. So what happens when he tries to accelerate downwards? So his mg is still 784 newtons. However, the normal force must now be smaller than your mg, such that there is a net force in the downward direction, which causes the acceleration a in the downward direction. So if you write the equation, it is going to be mg minus Fn, which is your net force, and that must be equal to ma. In rewriting this, you get mg minus ma equals Fn. So notice that in this case, your apparent weight is smaller than mg. So that means you're going to feel lighter than usual when it is accelerating in the downward direction. So going back to the simulation, let's repeat the ride. So you're on the first floor, and as you accelerate, your normal force increases, and then when you're stopping, your normal force is going to decrease, and then when you come back to rest, the normal force becomes equal to your usual weight. What happens if the elevator cable is cut off and you are actually accelerating downwards at a value equal to g? That means if a is equal to g, isn't that situation interesting? Use the formula to see what will happen if a is equal to g.